Hello guys, my name is Akash and welcome to your fifth Spark tutorial. Before we get started with anything, I wanted to apologize for such a long delay between tutorial 4 and tutorial 5. My last semester got kind of busy and then I moved, so it was a very busy time in my life and therefore I was not able to upload any tutorials. So now that I'm back, I'll try to upload all the tutorials on regular interval and hope they help you learn Spark. So let's get started. In tutorial 4, we covered basics of Hello World of Spark, which is a word count program, and we executed it on a Jupyter notebook, and then we learned how we can execute Spark programs from our terminal. We also explored how word count program would behave on a single node system, and we said that we'll explore how word count program would behave in a distributed environment in this tutorial. So let's get started. In this tutorial, before we explore anything, I just wanted to build upon our knowledge of what we know about RDD and Spark, and then we are going to talk about um, how a word count program would behave in a distributed environment, and how to deal with multiple input files, and what are the essential steps that we need to ensure when we have multiple input files. So let's get started. So first point that we are going to cover is that RDDs are immutable. What does immutable mean? Well, it just means that once an RDD is created or initialized, they cannot be altered. So one might ask, what happens when you want to do some transformation on RDD? Suppose if it's an integer RDD and you want to add 1 to every single integer, you want to map that function on RDD. What happens in that situation? Well, the concept is simple. Spark will basically create a new RDD using this transformation operation and store the results into this new RDD. It will not alter the previous RDD. And the way Spark does this, executes all of its program, is by constructing an operation flow. That operation flow is illustrated by Spark DAG. DAG is basically known as direct acyclic graph, and for those of you who are from a computer science background would know what a direct acyclic graph is. It is basically a graph which does not have cycle, and we don't want our programs to have any cycle, because if the program has a cycle, then it would basically run into an infinite loop at the time of execution and it will never end, and we want our programs to end. So it's essential to have this direct acyclic graph as your operation flow. So this is an example of direct acyclic graph where Spark basically has two different data sources, a text file and a Cassandra table. You read the data from these two different data sources. First you map on a text file, whereas you filter on a Cassandra table, make new RDDs and join them. Mapping and filter operations are covered in our previous tutorial, but joining operation is not, and we will cover that in our future tutorial. Once the join operation has been performed on our RDD, it will basically perform a map operation on this joined RDD and then eventually do reduce and save as text file. But if you remember, then before even anything executes on this operation flow, Spark has to be able to recognize an action in order to execute this operation flow, and you realize that reduce and save as text file are these actions. So as soon as Spark hits the action reduce, what would it do? It will ask the fundamental question that what do I need in order to complete this reduce operation? So the answer to that question is that you need this mapped RDD in order to complete this operation. So how do you get this mapped RDD? Well, you need this join RDD. How do you get this join RDD? You need this mapped and this filtered RDD. How do you get both of these RDD? You need to get it from these two data sources. You need to read them, and every single time an action is called, it will basically go through this entire workflow in reverse and try to construct back entire RDD till it can perform an action. So reduce will go all the way to reading the data source, and then when you want to execute save as text file, it will again go all the way back to this data sources, which is kind of like having a redundant operations every single time you want to perform some action and RDD. So how do you avoid this um, this redundant action? Well, so the simple answer to that question is just cache RDD. Whenever you know that you're going to be using this RDD more than one time, just cache them. And one simple standard that people generally follow in the industry is that as soon as you read from the data source and do some basic cleaning operation from on that data source that you read, just cache them, because reading from the hard drive is pretty expensive operation, or even reading from the Cassandra table involves going over the network, which is again expensive compared to having the data source into the memory. And that's why you want to make sure that all of your data is in memory whenever you want to do some sort of computation on your data source. So therefore, you should always do caching as soon as you load the data source, the data from data source, and do some basic operations, little bit of filtering and cleaning on the data source to be used. And whenever you know that you are going to be using the RDD more than once, it is recommended that you cache the RDD to avoid recalculation of the RDD. For example, this join RDD will be used twice in reduce as well as save as text file. So just cache this join RDD so that it doesn't go all the way back to entire operation flow. It will just ask the question, okay, if I want to perform this reduce operation, what do I need? I need a mapped RDD. If I want to perform this map operation, what do I need? I just need a join RDD. And if I want to perform join RDD, what do I need? Well, I already have a join RDD, so I don't need anything. I can use that join RDD and do my operations and finish off this reduce operation, starting from a map and a join and then a reduce, or map and a join and a save as text file, which will eliminate these redundant steps. Don't worry about it if you don't understand, but this is how you should utilize cache, and we are going to cover that in future tutorials whenever we can. um, I will try to use a cache when we have such type of flow. This is just another example, basically the same thing. You can try to do exercise by pausing the video and going through the operation flow of this Spark program. So last thing that we want to cover about RDD is something known as RDD lineage. So what does a lineage mean? It basically means that whenever Spark is executing a program, and suppose that RDD gets lost somehow, like even the cache RDD somehow can get lost, and Spark lost the RDD. How does it know that this RDD existed, and you know the data is basically gone, right? How can it reconstruct that RDD back, get that data back that it has just lost by accident? Well, it's just simple. You just go into this DAG operation flow, and then you basically say that, suppose you lost this joined RDD, you just say that, how can I get the joined RDD back? And the simple answer is just have this mapped and filtered RDD, and you basically join them and get this join RDD. And in order to have this two different RDD, you need to read from the data source, which is a text file and a Cassandra table. So that is a concept which is known as RDD lineage. It basically means that if you lose an RDD, Spark can always reconstruct that RDD back. And this concept is known as RDD lineage. Interview question, that's how they will ask you what is RDD lineage whenever you go into an interview. So yeah, you can memorize that or understand that. So finally, let's get started on the distributed environment and how a program would behave in a distributed environment. Okay, so the basic environment that we have in order to execute this program is that we have three different input text file, a master node, and three different worker node or data nodes in our cluster. So as we said, three different text file, a master node, and three worker nodes. So whenever we have more than one input files, what Spark tries to do is partition the data according to this input file. So one of this text file will read fully by master node and sent to this worker node fully, like the partition data will be from this file over here, and then second file will be stored here and third file will be stored here, and each of the file will be considered as a partition data itself. So whenever you're having more than one input file or multiple input files, it is essential to make sure that the file sizes are about the same, because if the file sizes are different, then Spark will need to repartition the data set, and that will be a pretty expensive operation. Suppose like you have this file to be 1 TB and two other files are just 1 MB, then not only it will take more time to read the data from the file and partition it, but it will also take time to repartition the data source. So just make sure that it's evenly distributed so that parallel reads can happen, and then partition can be easy, and the whole parallelization of Spark is utilized. That's the point of using Spark, because you want to have that parallelism achieved, and to do that you need to make sure that you have some sort of similar input size files so that they can be read in parallel. So once the partition of the data has happened and this is our cluster, it will be formed into RDD like this ones. If you saw our previous input file, it basically started off as Apache, Spark, 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 which is first file line from our previous input file. I copied the input file 3 times to have 3 different input files, so we basically have the same load on all of our 3 different input files, and they are stored in one RDD each in an input file. This is just one way of doing it. I mean, definitely Spark cluster can have a different approach to the distributed execution of a program, but just assume that this could happen because this is pretty easy, and this does happen when file sizes are about same. This is how Spark partitions the data. So after that we apply some sort of initial filtering and some sort of mapping operation where we say that okay, this is just convert all the words to the lower and put a 1 next to all the words, which basically says that this word happened once. The occurrence of the word is over here in the 1. And after that we can get started with our operation of doing word count, where we can reduce by key like we explored in our previous program. So there are multiple ways to do this reduce by key operation. One is simply how basically Suppose that sorry for changing the slides so often, but you can send this Apache keywords or A to say the keywords that start with A to H can be sent over to this server, and then I to maybe O or P can be sent to this server, and then rest the words can be sent to this server, and they will add them up and then give you results, which would be a very long way. There are multiple, I mean, definitely multiple ways to calculate results, and we want to um, be as optimized as possible because network bandwidth is a main issue, and they are pretty slow compared to your memory. So something known as a combiner will be used in order to speed up the execution of the program in order to efficiently execute this reduce operation. So what is a combiner? A combiner is basically a copy of your reduce operation, but at a worker level node. So instead of sending this 111 over to the network from this one to over here, Spark to over here, Spark 1 to over here, what you do is you basically combine them at individual nodes. So it's like running a single node word count program here, a single node word count program here, and a single node word count program here, like we ran last time on a single computer, and then getting a results over here, which is what we got the last time, our results. And then once you have this entire results, you can send over this Apache 25704 over the network, which will basically eliminate this Apache, 1 being sent over 25,000 times over the network. Imagine how much time you have saved by just eliminating this 25,000 times word exchange to different computers. And I mean, you're looking at 50,000 different, 51,000 word exchange over here. Had Apache been transferred to this computer without being reduced at individual computer nodes. So we basically save some time by executing combiner, which is just like reducer. And there are instances where combiner can be different than what a reducer looks like. So you need to ensure, like, combiner is okay. That is the case when you're writing Hadoop program. You would be writing some sort of combiner as well at a map operation. But again, I mean, Spark is a high level framework, and it does not require you to write combiner in general cases. It takes care of the combining part by itself, so which is good part. And optimization is done by Spark, so you don't need to worry much about that. So now what happens? So once we have this data calculated, it basically performs the reduce operation, which we just talked about. Sends A to I over here, J to S to this node, and then T to Z over here. So all the word that starts with A are sent to this node. All the word that starts with J to S are sent to this node. All the word that starts with T to Z will be sent over to this node. So all the Apaches and highs are sent over to this node from these two different nodes, which is this two different worker node will be sending this Apache and high keyword to this node over here, and Spark will be sent to this node over here, a tutorial will be sent to this node over here, and so on and so forth. And you can see how it has reached over here. And now what happens is that you run a word count program at single node again with this um, respective word count, like we did for a single node computer, which is basically uh, the distributed programming behavior. So basically, when you run a word count program, you would add all these three word up because it's a single word, and then you have around 70 like 76,000 something, and same happens with Spark 76,000 something, Tutorial 76,000 something. Sorry, it would be 77,012. 77,012 would be the answer for the number of occurrences of Apache, Spark, and Tutorial in this the reduce tab. And then eventually what happens is that you want to find out the result. So Apache is stored over here, Spark is stored here, Tutorial is stored here. How do you find out the results? Generally, as I said, using collect is a very bad practice, and you should not use collect, because suppose you have like millions and millions and millions of words over here, and then same everywhere, and it's just too much of memory that your masternode can take. And if you call a collect, your program will basically crash, because it will run out of memory on your masternode. So what should you do? You should basically coalesce, which we'll cover in or I think we have covered in previous tutorial, and basically save it into a text file, and then try to read from that text file what the result is. And that's how a word count program would behave in a distributed environment. Well, this is just the overview of how distributed systems execute the program, especially Spark program, and it's not a detailed overview, and it's not limited to this as well. So you could explore more on this, but this is just to give you a basic idea that how distributed systems tend to behave when they have to deal with multiple input sources, and they have to deal with similar type of operation on all different nodes. What are the type of optimization techniques that can be implemented, and what are the techniques that what are the practices that are bad practices in distributed system. When you're writing your code, you need to make sure that that does not happen. um, Definitely these techniques and bad practices as well as good practices are not limited to what we just studied in this tutorial. There is much more to learn than just this much about distributed system, which in itself is a very fascinating topic, and if you should explore more. But for the purpose of our tutorial, with this much of knowledge, you should be fine, and you should be able to study and take more tutorials. So in next tutorials, we are going to be covering some complex operations that we can perform on our RDD and do calculations. And yep, so I am running out of time, and so we are gonna stop this tutorial. Give this tutorial thumbs up, subscribe to my channel, and please comment if you have any question. I will try my best to answer them as soon as possible. Thank you for watching the tutorial.